So now let's check some differences between mixtures and compounds. The proportions. So let's take water or H2O as an example. Water molecules will always have 2 hydrogen and 1 oxygen atom, but a mixture of hydrogen and oxygen can have any number of molecules. Properties. In a mixture, all elements keep their own properties, but in a compound, their properties change. For example, iron and sulfur mixture means iron is grey and sulfur is yellow, but in the compound iron sulfide, it's either black or brown. And finally, separation, or ease of separation. A mixture can be separated by physical means, but a compound cannot be separated by physical means. You should use electrolysis. While we're on the topic of separating mixtures, let's look at different methods to separate mixtures. Filtration can be used to separate a solid from a liquid. The substance left in the filter paper is called a residue, mostly solid, and the liquid that goes through is known as the filtrate. Remember, this is for insoluble solids. Crystallization is the process of heating a solution to boil off some water until the solution is more saturated, and then turn off the heating and let crystals form. Then you can filter and dry the crystal. This is for soluble solution. But if you want to collect the liquid too, you can use simple distillation. In simple distillation, when the water is heated and turns into water vapor, it will go into a condenser where it will cool down and come back to the liquid form, and we can collect it in the beaker next. So last but not least, chromatography. You can use paper chromatography to separate most inks and food coloring made up of more than one type. In chromatography, separation is achieved due to difference in solubility. The mass of an atom is very small. For example, a hydrogen atom's mass is 1.6 into 10 to the power minus 24 grams, which is pretty tiny. So to make it easier, scientists have a separate unit for atomic mass. It is called Atomic Mass Unit, or AMU. It is defined as 1/12 of the mass of the carbon-12 isotope. Now before we move into relative atomic mass, we must take a look at isotopes. Although isotopes are explained in another video, the basic understanding is isotopes are atoms of an element with the same number of protons but a different number of neutrons. So isotopes would have a different mass. They also have a different abundance. Now relative atomic mass is the weighted average mass of the atom divided by the AMU, which is 1/12 of the mass of the carbon-12 isotope. For example, oxygen's relative atomic mass is 15.999, which is rounded to 16. Another way to find the relative atomic mass is through the relative isotopic mass. So you'll remember that isotopes have different mass and abundance. Taking chlorine as an example, one chlorine isotope would have a relative isotopic mass of 35 and an abundance of 75%. The another chlorine isotope has a relative isotopic mass of 37 and an abundance of 25%. The relative atomic mass would be calculated as 35 into 75 plus 37 into 25, and all that divided by the total abundance, which is 75 plus 25, so 100. The answer would be 35.5. Next, relative formula mass. An easy way to explain this would be using an example: calcium carbonate. First, you find the relative atomic mass of each atom, which you could read from the periodic table. Calcium 40, carbon 12, and 3 oxygen, so 16 into 3, which is 48. Next, add them all up, making the relative formula mass 100 for calcium carbonate. If we look at water, there is strong covalent bonds between the H and O atoms. But it is the intermolecular attraction force that holds all the water molecules, all the H2Os, in place in a liquid state. These intermolecular forces are pretty weak. So when a physical change such as boiling or freezing happens, it is the intermolecular forces that are broken, not the covalent bonds. A substance with molecules with intermolecular forces between them are called simple molecular structures. H2O, CO2, CH4, NH3 and C2H4 are just some examples of simple molecular structures. Here are a few properties of simple structures. Firstly, substances with simple molecular structures tend to be gases, liquids or solids with low melting and boiling points. Next, as the relative molecular mass increases, the intermolecular force increases as well. Simple molecular substances do not conduct electricity due to the fact that covalent substances do not have an overall electric charge. Covalent molecules are usually insoluble in water. Next, we are going to be talking about giant covalent structures. Diamond is a form of pure carbon. It is a giant covalent structure. Each carbon has 4 electrons in its outer shell and therefore forms 4 covalent bonds. In a diamond, each carbon atom bonds strongly to 4 other atoms in a tetrahedral arrangement, as you can see in the diagram. Here are some of the properties of diamond. Diamond has a very high melting and boiling point. In general, all substances with giant covalent structures are solids with high melting and boiling points because a lot of energy has to be supplied to break all the strong covalent bonds. Diamond is very hard, and diamond does not conduct electricity because all the electrons in the outer shell of the carbon atoms are tightly held in covalent bonds between the atoms. Graphite is another form of carbon, but the atoms are arranged differently, although it still has a giant covalent structure. Graphite is a soft material. Although the forces holding the atoms together in each layer are very strong, the attraction between the layers are very weak. Graphite is mixed with clay and used in pencils as the lead. Graphite has high melting and boiling points. Graphite conducts electricity. It is one of the only non-metals that conduct electricity. Along with diamond and graphite is C60 fullerene. But a difference between C60 fullerene and diamond and graphite is that C60 fullerene has a simple molecular structure in contrast to diamond and graphite. In a solid or liquid C60 fullerene, there are C60 molecules with weak intermolecular forces between them. The fact that C60 has a simple molecular structure has a big influence on its properties. Let's take a look at them. 660 fullerene has a lower melting and boiling point than diamond and graphite. 660 fullerene is not as hard as diamond, and C60 fullerene does not conduct electricity. We call the elements in group 1 alkali metals, consisting of lithium, sodium, potassium, rubidium, cesium and francium, the last of which is radioactive. Here are a few important facts about alkali metals that you must keep in mind. The melting and boiling points get lower down the group, so lithium has a higher melting point than potassium. The density increases as you go down the group, but not regularly. All alkali metals are soft metals and they get softer as you go down the group. Another fact would be that the reactivity increases down the group. All these metals react with oxygen quickly to form oxides and have a rapid reaction with water to form strong alkaline metal hydroxide solutions. This is the reason behind group 1 metals being called alkali metals. Due to their rapid reaction with water and oxygen, which are both present in air, lithium, sodium and potassium is stored under oil. Rubidium and cesium are so reactive that they have to be stored in sealed glass tubes. Now let's take a look at some of the most common properties of alkali metals. They all have one electron in the outermost shell. Sodium 281, potassium 2881. They all react with water similarly to form a metal hydroxide and hydrogen gas. They all react with oxygen to form an oxide. They all react with halogens, the group 7 elements, the same way, forming halides, and all group 1 metals form 1+ ions. Using all the information mentioned before, Let's take a look at the reaction of alkali metals with water. The equation is the same for each metal. 4 alkali metal plus water arrow 2 alkali metal hydroxide plus hydrogen. The difference between the reaction is the speed, as the reaction of alkali metal increases as you go down the group. When sodium reacts, here are the main observations you can see. Sodium floats because it is less dense than water. Sodium melts into a ball because its melting point is low and a lot of heat is produced by the reaction. There is fizzing because hydrogen gas is produced. The sodium moves around on the surface of the water. The piece of sodium gets smaller and eventually disappears because the sodium is used up in the reaction. If you test the solution with universal indicator, you will see that the universal indicator goes blue, meaning that this is an alkali solution. The metal hydroxide is alkaline. Now that we took a look at the reaction with water, let's look at alkali metals reaction with air, or more specifically oxygen. As soon as an alkali metal is cut, its surface will be shiny, but it will soon get tarnished due to its reaction with oxygen in the air. If we heat the alkali metals, there will be a rapid and more vigorous reaction. Lithium will burn with a red flame and form lithium oxide. Sodium burns with a yellow flame to form sodium oxide, and potassium burns with a lilac flame to form potassium oxide. Group 1 metals are silver grey. The group 1 metal compounds are white solids and they dissolve in water to form colorless solutions. Before we watch this video, I'll recommend you watch our Intro to Organic Chemistry video. But if you already know about the basics of organic chemistry including isomers, then head right in. Alkanes are saturated hydrocarbons. This means that they only have single bonds in their structure, so that every carbon atom has 4 single bonds. They also have a tetrahedral arrangement. The general formula for alkanes is CnH2n plus 2. This means that any alkane which has 2 carbon atoms would have 6 hydrogen atoms, C2H6, which is ethane. Now let's take a look at some reactions involving alkanes. The first reaction would be combustion. As you probably already know, there is complete combustion and incomplete combustion. When an alkane reacts with sufficient amount of oxygen, carbon dioxide and water is produced. This is complete combustion. If methane reacts with oxygen, it produces water and carbon dioxide. If ethane reacts with oxygen, it also produces water and carbon dioxide, just different numbers. Similar to complete combustion, if there is limited oxygen, incomplete combustion occurs. The product is similar, but instead of carbon dioxide, carbon monoxide or carbon soot is formed. Here's the equation for methane and ethane, but incomplete combustion. Another reaction that involves alkane is substitution, or more specifically halogenation reaction. As I mentioned before, alkanes are saturated, so there must be UV light during a halogenation. Here's an example. Methane plus bromine is bromomethane plus hydrogen bromide. Here's a visual representation to help you get a better understanding. Let's take a look at another example. Propane plus bromine. How will you know which hydrogen's place this bromine is going to replace? You will know that from the name. If the bromine replaces a hydrogen in the first carbon, it's called 1-bromo. The bromine replaces a hydrogen in the second carbon, 2-bromo, and so on. Remember, this applies to all the halogens, group 7 elements, reacting with an alkene. Starting with hydrogen. The test for this is simple. Hold a lighted splint at the mouth of your sample. If hydrogen is present, the splint will go off with a squeaky pop. For oxygen, hold a glowing splint towards the sample. If oxygen was present, the splint will relight. Next, carbon dioxide. If carbon dioxide is bubbled through lime water, the lime water would become milky or cloudy. damp litmus or universal indicator paper would first turn red and then get bleached for chlorine gas. Simply use universal indicator or red litmus for ammonia. It will turn blue. Moving on from gases, we'll now look at the test for water. Anhydrous copper 2 sulfate will turn blue from white if water is present. Here's the equation that is used to show that. Also, this test does not show that the water is pure, since it works for any substance that contains water. Now let's see the testings for ions, which are positive ions, negative ions, the ones which we discussed in the ionic bonding video. So the first method we would use is a flame test. A flame test has a platinum or nichrome wire dipped into concentrated hydrochloric acid and then into the salt that you want to test, so that some salt sticks on the end. The wire and the salt are then held just within a non-luminous Bunsen burner flame, and then the color is observed. So if there is lithium ions present, the flame would turn red. Yellow shows that there is a presence of sodium ions. Lilac means that potassium ions are present. Orange-red color meaning calcium ions are present. A blue-green color would show that copper 2 ions are present. While we are on the topic of ions, let's see how cations will react with sodium hydroxide solution. So, if copper 2 plus ion is present, there would be a blue precipitate forming. The name of the precipitate would be copper 2 hydroxide. If the ion Fe2+ is present, a green precipitate will form, with iron 2 hydroxide formed. Fe3+ means an orange-brown precipitate will be formed. We call this iron 3 hydroxide. And if we try an ammonium ion, that is NH4+, an ammonium gas is produced. There will be no precipitate here. To test for carbonate, we first add some dilute hydrochloric acid. If there is fizzing or effervescence, you would know that a gas is given off. Then test the gas for carbon dioxide by bubbling it through lime water. If it turns cloudy, then carbon dioxide is present. The sample is a carbonate. For testing for sulfates, the salt must be added to hydrochloric acid and then to barium chloride solution. If sulfate ions are present, a white precipitate will be formed. Just a note, when adding an acid to the salt, do not use sulfuric acid as that contains sulfate ions on itself. Finally, testing for chlorides, bromides and iodides. For all three of these halide ions, you must add nitric acid followed by a silver nitrate solution. If chloride ions are present, you would notice a white precipitate forming. If bromide ions are present, a green precipitate will form. And if iodide ions are present, a yellow precipitate will form. For sulfate and halide ions, the test acid is added to remove interfering ions like carbon ion from the test solution. Specific heat capacity is the amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. SHC is measured in joules per grams per degree Celsius. So when it comes to measuring the enthalpy changes, that is how much heat given in or taken out during a reaction, we can use a simple formula. Q equals mc delta T, or heat energy equals mass into specific heat capacity into temperature change. Now that we've got the equation, let's take a look at the experiments that we'll have to carry out. The technique for this, calorimetry, is that we use the heat from a reaction to heat another substance and then use the Q equals mc delta T equation to calculate the heat released. For this method, the mass, SHC and temperature change are all of the substance heated. If you find this confusing, don't worry, let's do a calorimetry experiment for combustion.
For this simple calorimetry experiment, looking at the combustion of alcohols, we have a copper calorimeter, a lid and a stirrer, a 0 to 100 centigrade thermometer, and we've got a spirit burner containing ethanol. In this experiment, we're going to take 120 centimetres cubed of water and place that in the calorimeter. We then reposition the lid and the stirrer. We need to lift the thermometer up from the base about a centimetre or two and allow the equipment to equilibrate with room temperature. This one is reading 26 degrees centigrade on this thermometer. Check that the thermometer moves, stirrer moves freely. We then weigh the spirit burner. This one is 192.34 grams. 192.34 grams. We then light the burner, place rapidly underneath the water, start stirring with the stirrer, and measure the temperature increase of the water during the experiment. We started at 26, we're now at 32, coming up to 33, so we'll extinguish the flame. And it's important to keep stirring because heat has been transferred to the copper calorimeter and the water will continue to rise in temperature as that heat spreads throughout the system. So in fact we've now reached 34, just about, but then looks as like that's as much as we're going to get. Actually 33 and a half. No, 34, we were right, 34.
Since combustion is an exothermic reaction, the temperature of the water goes up. When we apply our data to the Q equals mc delta T equation, mass would be 120 grams as the density of water is 1 gram per centimeter cube. The temperature change would be 34 minus 26, so 8. The SHC of water is 4.18 joules per grams per degree Celsius. So we'll substitute all our values and multiply, and our final answer would be 4012.8 joules. The heat gained by water is 4.0128 kilojoules. The rate of reactions is the speed at which the amount of reactants decreases or the amount of products increases. It is measured using the change in concentration, volume or mass divided by time. If we conduct an experiment of a reaction between calcium carbonate and hydrochloric acid and measure the mass of the carbon dioxide produced, this is how it would look on a graph. So to calculate the average rate of reaction, we divide the mass of carbon dioxide produced and by time. So the average rate reaction in the first and second minute could be calculated like this. So we can see that the rate of reaction is fast at the beginning and slows down before finally stopping. This is because the reactants are getting used up during the experiment and the experiment stops when one or both reactants get used up. We can explain what happened using the collision theory. Collision theory states that reactions can only happen when particles collide, but the particles have to collide with a minimum amount of energy, called the activation energy. The collisions with energy greater than or equal to the activation energy are called successful collisions. So, in the before mentioned experiment, the acid particles have to collide with the particles of the marble chips. As the acid particles are used up, the collision rate decreases and the reaction slows down. Some of the factors that affect the rate of reaction are surface area. Larger surface area, faster the rate of reaction as the frequency of successful collisions increase. Concentration. Higher the concentration, higher the number of particles in a fixed volume, faster the rate of reaction as there are more successful collisions every second. Temperature. Higher the temperature, faster the speed of the particles, faster the rate of reaction. Another reason for increased rate of reaction due to the temperature is the particles get more energy, so the number of particles with enough energy to overcome the activation energy increases. Pressure. Higher the pressure, closer the particles are. Faster the rate of reaction, as they will collide more frequently. Catalysts are substances that speed up chemical reactions but aren't used in the process. This means the catalyst still remains chemically unchanged at the end of the reaction. Hydrogen peroxide can be split into water and oxygen using the enzyme catalase. Enzymes are biological catalysts. This reaction is almost explosive and produces a lot of heat. Here's the equation for the decomposition of hydrogen peroxide. We don't write the catalyst down because it remains chemically unchanged. Collisions have to have energy greater than or equal to the activation energy for a successful collision to take place. The way catalysts work is they speed up the reaction and provide an alternate route with a lower activation energy. The lower the activation energy, more collisions are likelier to be successful.